Welcome back to our Chem 152 video series. In previous videos, we found the pH of strong bases, strong acids, weak bases, and weak acids. In this example, we'll find the pH of a mixture of weak acid and weak base called a buffer. First, we're given the Ka value for HClO. I will tell you that is a weak acid because we do have a Ka. We are also told that we are placing some amount of HClO and NaClO in a beaker and allowing them to react, and we're meant to find the pH. Let's have a look at what we're putting in the beaker here. We have HClO, which is a weak acid, and we're adding NaClO in with it. Now, remind yourself that NaClO will break into Na plus and Clo minus, because it is soluble. However, as always, the Na, since it's a 1A metal, will not influence the acid or base activity here, leaving us really with just Clo negative. Now, most things that are negative are weak bases. And since Clo negative is not on our super weak base list that I gave you previously, we'll say that this is a weak base. Now notice that these two compounds we've placed together are conjugates of each other because they only differ by H. Now, if you take a weak acid and put in its conjugate weak base, what you end up with is a buffer. Buffers are special mixtures of acid and base that resist change to their pH, meaning you could take a buffer solution and add some weak acid or some weak base to it, and the pH would not move by very much. Now, the pH of a buffer is governed by this equation. pH will equal negative log of Ka of the acid plus log of the moles of weak base divided by the moles of weak acid. Now, we were given our Ka value of 3.0 times 10 to the negative 8. Therefore, we know the Ka. We'll check that off. We also can find our moles of weak base. Our weak base was ClO, and we have 25 milliliters and 0.1 molarity of it. If we multiply those together, we will get 2.5. Since we are in milliliters, this will give us millimoles. If you want to change this to scientific notation, we can say 2.5 times 10 to the negative third moles. Either one in this equation is fine. If you want to use millimoles, you can. If you want to use moles, you can. I'm going to simply use moles here to avoid any further confusion, though. To get our moles of acid, notice that we do have 100 milliliters and 0.1 molarity of HClO. This will give us 10 millimoles. If we want to change this to scientific notation, we can write 10 E negative third moles. While this is not proper scientific notation, you'll see how this works in a moment. We'll check off our weak base and weak acid, and let's put the numbers into this equation. We'll say pH is equal to negative log of 3.0 times 10 to the negative 8th, plus the log of the weak base, which was 2.5 times 10 to the negative third, divided by 10 times 10 to the negative third. The reason why I input the numbers this way is to show that if you have 10 to the negative third on the top and the bottom, they cancel out, and we can just write 2.5 divided by 10 inside of the log. We can place all of this into the calculator at once. We'll end up with a pH of 6.92. So for this particular buffer solution, we'll have a pH of 6.92. And so now we know the pH of this buffer. There's a second way we may make a buffer. Method number 1 was to add a weak acid and its conjugate base. In this question, we'll use another method, which involves taking our weak acid, HClO, and now adding a strong base. Now, bear in mind that NaOH will break into Na plus and OH minus. Na plus will not have any acid or base activity, so what we're going to do is react our HClO, our weak acid, with OH negative, which is a strong base. Our weak acid will lose an H and become ClO negative. Our strong base will gain an H and become water, H2O. Now that we know what happens, let's figure out how much product we make. To begin with, let's find the moles of our weak acid and our strong base and figure out which one runs out first. This is similar to the limiting reagent problems you may have done in your previous semester in Chem 151. Our weak acid has 100 milliliters and 0.1 molarity. If we multiply these together, we will get 10 millimoles, which is the same as saying 10 times 10 to the negative third moles. We'll write that underneath our weak acid. Now we'll do the calculation for the weak base as well. Our weak base has 25 milliliters and 0.1 molarity. This will give us 2.5 millimoles or 2.5 E negative third moles. We'll place that underneath the OH minus. ClO negative starts at 0 because I didn't give you any to start with, and water will not affect the equilibrium at all, and so we don't have to write anything for it. If we examine the numbers underneath HClO and OH negative, we can see OH negative is smaller, and so we will lose all of it. The reason why we know we lose all of it is because that strong base drives the reaction forward, and that this reaction will be very, very favorable because of that strong base. You may notice that I only used a single arrow to show this reaction, and that's because it is very favorable thanks to the strong base. Because this reaction is favorable, we will assume that we will lose all of the strong base and lose exactly the same amount of the weak acid. Notice that we don't lose all of the weak acid, we only lose as much strong base as we had. This also means we'll gain some HClO negative. So based on our initial amounts of moles, we can find that the change is whichever amount of moles is lower. We lose both reactants and gain some product. So if we do the additions and subtractions, we'll end up with 7.5 times 10 to the negative third molarity moles of HClO. We end up with no OH left over, but we do get some ClO negative in return. Notice that now we still have weak acid left over. We don't have any strong base anymore, but now we do have weak base to go with it. And notice that our starting acid and our product base are conjugates. And so because these are conjugates, we still have a buffer. Based on the fact that we still have a buffer, we can still use our buffer equation. Our buffer equation still says that pH is equal to negative log of Ka plus the log of weak base divided by weak acid. We have the Ka, we'll check that off. We have the weak base, check that off. And we have the weak acid, check that off. So now we can say that pH is equal to negative log of 3.0 times 10 to the negative 8 plus log of 2.5 times 10 to the negative third divided by 7.5 times 10 to the negative third. The 10 to the negative thirds cancel out, and so we can write 2.5 over 7.5. And then we can enter all of this in a calculator. We'll end up with a pH of 7.05. And so now we know how to get the pH of both types of buffers. The first type of buffer we did was a weak acid and a weak base that were conjugates. Our second form was a weak acid plus a strong base, which reacted together to give us a buffer solution, even though we didn't start with one. Now be careful about this equation. This equation is only good for buffers. This means you must have a weak acid and its conjugate weak base together in order to use this. If you don't have a weak acid and a conjugate base together, this formula will not help you at all. So make sure to verify that you do in fact have a buffer before attempting to go to this equation. Thank you for watching, and we'll see you again soon.